All right, today we're going to talk about skeletal structures. And skeletal structures should end up being a more robust and a faster method for drawing Lewis structures. And so we're going to go through today and learn what a general method is for all these, draw a couple skeletal structures, have a good strategy as we go forward, and then go back through and redraw all the Lewis structures that we've done previously. All right, so whenever we're drawing a skeletal structure, sometime you'll be given a structural formula where the atoms are listed in such a way that it tells us what order they occur in. Other times we're going to have to try to make the molecule as symmetric as possible, but as we practice more and more, your chemical intuition will be growing. So what we really want to start out with is to distinguish between central and terminal atoms. So a central atom is one that's bonded to two or more atoms. So if you ever see that you have a carbon atom, it's your central atom. In terminal atoms, if you see a hydrogen, that's always going to be a terminal atom for us. But otherwise, there's some wiggle room for all the other ones. So let's go ahead and look at a few hints, draw out some skeletons, then further our strategy. So again, like I said, hydrogen atoms are always terminal atoms. If you have a choice between what your central atom is, always choose the one with the lowest electronegativity, or another way of saying this is the more electropositive atom. Carbon atoms are always the central atoms. And then, if possible, we are going to try to have some sort of symmetrical or compact structure. So let's go ahead and look at a few examples. We won't draw the full Lewis structure. We're just going to draw the skeleton at first. But so for HCN, so this would be a structural formula. So we would line up the atoms in order. So we have H, C, N. Okay, and then what about CO2? Okay, so you might start out by drawing the skeletal structure like this, COO. But you probably only do that if you think you're cool, because we're going to try to have symmetric molecules when possible. So we would have OCO as our structure there, our skeletal structure. If we were to look at our next one, CH3OH. Okay, so CH3. We know carbon's going to be our central atom. So that H3 signifies that there's going to be 3 hydrogens surrounding the carbon. And then we'll have an oxygen and then a hydrogen. Okay, so that's the general skeletal structure for methanol there. And then for ethanol, the next one, we have CH3, CH2OH. So we have CH3 looking like this. Then we have our CH2. And then we have our OH. So what we'll do is we'll go ahead and finish up our strategy, and then we will go through and draw all of our Lewis structures using this method. So again, the first thing you want to do is determine the total number of valence electrons. If you have a charge, make sure you're accounting for what was lost or what was gained. Try to identify your central atoms and terminal atoms. So if you have a carbon, you know it's central. If you have hydrogens, you know they're terminal. Otherwise, you have to go off of what's more electronegative tends to be your terminal atoms. So, more electronegative. After you draw your skeleton, the first thing you'll do is you'll go through and add single bonds. Remember that for each bond, there are 2 electrons there, so you'll subtract those 2 electrons from the total number of valence electrons. After you've done that, you will complete the octets of the terminal atoms first, and then you will go to the central atoms if you can. But whenever you are adding the electrons to the terminal atoms, start with most electronegative first. Okay, and then if you have one or more central atom left with an incomplete octet, we're going to have to move a lone pair of electrons to form a multiple covalent bond, so a double or a triple bond. All right, so let's go ahead and go back and go through all of our examples, and we'll try to use this strategy. That might have been too far. All right, so let's look at F2. So how many valence electrons do we have? Well, we have a total of 14. So if we were to draw our skeleton, this is fairly easy. We just have 2 fluorines. So the next thing that we'll do is we'll add a single bond here. So that takes us down to 12 valence electrons. And then we will add our lone pairs. So how many lone pairs can the fluorine on the left take until it has a completed octet? Well, remember we count the bond as 2 electrons, so we have 1, 2 valence electrons there, then 3, 4, 5, 6, 7, 8. Okay, so we've added 6 valence electrons, so we're down to 6. So the remaining 6 go on this fluorine. Then what we'll see is now we have a good Lewis structure. We have a completed octet, we have a single bond, we have all of our electrons are paired. So we're done. We didn't even have to draw out the Lewis symbols to start with. Let's go ahead and look at CH4. Okay, well here, carbon has 4 valence electrons. We have 4 hydrogens each with 1. So that's a total of 8 valence electrons. So if we were to draw out our skeleton, we know carbon has to be our central atom. And we know that this is not an acceptable skeletal structure because hydrogen can only be a terminal atom, and if we went through and added single bonds, that would make hydrogen a central atom. So this is not a good skeletal structure. So what we need to do is we'll have carbon, then we have 4 hydrogens surrounding it. Go through and add our single bonds. 2, 4, 6, 8 valence electrons have been used. So we've used all those valence electrons, and we're done. So that's, yet again, another good Lewis structure. Let's go on to another one. We have water. Hydrogen has 1 valence electron, oxygen has 6, so that's a total of 8 valence electrons. If we were to draw our skeleton, we know we'll have oxygen, and then we'll have hydrogen. Okay, and again, hydrogen has to be a terminal atom, so we'll draw the skeleton like this. We'll add 2, 4. We'll use up 4 of our valence electrons there, so 8 minus 4 is 4, so we have 4 remaining. Now we cannot add any of the valence electrons to hydrogen because hydrogen already has its outer orbital filled. Hydrogen can only have either a lone pair or a single bond to it. It can't accommodate any more electrons. So that means we'll have to start adding our electrons to oxygen. So we have 4 electrons that we can add, so we can add 2 lone pairs. Okay, so now we've accounted for all of our valence electrons. Hydrogen's in good shape. Oxygen obeys the octet rule, so boom, roasted. We have a good Lewis structure. Let's look at HF really quick. Hydrogen has 1 valence electron. Fluorine has 7, so this is a total of 8 valence electrons. If we were to draw out our skeletal structure, we have HF. We'll add our single bond, which takes us down to 6 valence electrons, and then we'll put around the more electronegative atom first, which is fluorine. So 1, 2, 3, 4, 5, 6. Fluorine has a completed octet, and then we have no unpaired electrons, so we're in good shape. So now let's go ahead and try to do this for things that may have a formal charge on them. So let's look at NH4+. So how many valence electrons do we have? Well, we have 5 from the nitrogen plus 4 from the hydrogen, but then we're losing 1, so that's a total of 8. So if we were to draw our skeleton, we're going to try to draw this with as much symmetry as possible. We're going to have NH4 that looks like this, because again, hydrogen has to be a terminal atom. We'll go through and add single bonds, 2, 4, 6, 8. So we're down to no valence electrons left. Okay, so then we know there's going to be a charge on this, so you'd have to go through and determine that, well, nitrogen is supposed to have 5 valence electrons around it, but for the formal charge, the bonds only count as 1. So we have 5 minus 1, 2, 3, 4. So nitrogen has a +1 charge. All right, so now we're going to go ahead and look at using this skeletal method for drawing multiple bonds. And at first, this may seem more difficult than what we did at first with the Lewis symbols, but as we get more complicated molecular formulas, this will end up being easier for you in the long run. All right, so for oxygen, each oxygen atom has 6 valence electrons for a total of 12. So what we'll do is we'll go ahead and draw our skeletal structure that looks like this. Ooh, scary. And then what we'll do is we'll add a single bond. So that takes care of 2 electrons. So we're down to 10. And now for filling up the octet, you have to fill up one of the octets completely before you go to the other. So for instance, what I would do is we have 10 valence electrons remaining. So complete the octet for the oxygen on the left first. So we have 2, 4, 6 valence electrons used up. Then we only have 4 left over for this oxygen. Okay, so as you're looking at this, one of the things that you'll probably notice is that it's not symmetrical. So we are always looking for something that's symmetric if possible. So as we look at this, let's try to go through and look at the formal charge. So we know that oxygen, if we drew out the Lewis symbol for that, is supposed to have 6 valence electrons around it. So if we look at the oxygen on the left, remember that the lone pairs count as 2 electrons. The bonds count as 1 for the formal charge, so we have 2, 4, 6, 7. So, and then there's only supposed to be 6, so 6 minus 7, so we have -1 as our formal charge on oxygen. Then the oxygen on the right has all sorts of things wrong with it. It doesn't obey the octet rule, and it's supposed to have 6 electrons around it for the formal charge, but it only has 1, 2, 3, 4, 5, so it has a +1 formal charge. So what we can do whenever we have adjacent atoms that have oppositely charged, opposite sign or opposite formal charges, what we can do is we can move a lone pair of electrons in, and what we'll get is this. So now both oxygen atoms obey the octet rule, because for looking if something obeys the octet rule, we count the lone pairs as 2 electrons. The bonds count as 2 as well, so each oxygen, if we were to take away the one on the right, we have 2, 4, 6, 8, so that one obeys the octet rule, the same on the right. So we're in good shape there. Okay, and the formal charge is 0. Each oxygen is supposed to have 6 electrons around it. And then remember, for formal charge, the bonds only count as 1 electron, so we take 6 minus the 4 from the lone pairs and the 2 from the bonds, so we have no formal charge on oxygen. So that's a good Lewis structure. Let's go ahead and go on to nitrogen. So here we have a total of 10 valence electrons. If we draw out our skeleton, we have N, N. So first thing we do is draw a single bond. That drops us down to 8 valence electrons. And now we're going to fill up the octet on one of these atoms. So we have 2, 4, 6 electrons used on that one. You could fill up the one on the right if you prefer. Sorry. 8 minus 6 is not 6, it's 2. So we have a lone pair of electrons left to put on that nitrogen atom. So now what we need to do is let's figure out, do they obey the octet rule, and then do we have a formal charge? So the nitrogen on the left obeys the octet rule. The one on the right does not obey the octet rule. The nitrogen on the left is supposed to have 5 valence electrons, but it has 7 for the formal charge, so we have a -2 formal charge on the nitrogen on the left, and the one on the right is supposed to have 5, but there's 3, so this has a +2 formal charge. So what we can do, and I would always recommend moving one lone pair at a time, is start by moving one lone pair of electrons in. So we'll end up with something that looks like this. Okay, so as we look at this Lewis structure, we can see that it's not symmetric. The nitrogen on the left still obeys the octet rule. The one on the right does not obey the octet rule yet. Let's check out the formal charge. The formal charge on the nitrogen on the left is -1. Formal charge on the nitrogen on the right is +1. So what we can do is we can go ahead and move one more lone pair. You're always going to move the lone pair in from the species that has the negative formal charge. And we'll end up with this Lewis structure, which is symmetric. Everything obeys the octet rule. There's 0 formal charge, so we've minimized that formal charge. So this is a good Lewis structure. All right, so what I would encourage you to do is to draw this molecule by yourself, phosphine, pH3, and then go ahead and try to draw the Lewis structure for all those skeletons that we already drew and see if there's any multiple bonds that needed to be formed or not.